name is Evelina Palkanoglou. I am a structural civil engineer and I also hold a PhD in computational mechanics. Today, we will see how to use the nonlinear analysis functionality in advanced design, and also we will study thoroughly some of the cases where linear analysis is needed in order to produce effective and appropriate results. These three cases we will go through today is the generalized backlink, the second order analysis, the p-delta effects basically, and the advanced supports. And we will spend some time to discuss the different options the software provides in terms of the advanced supports and the engineering problems that can be modeled when using the advanced supports provided within the interface of the software. Starting with the generalized backlink analysis. The generalized backlink analysis can give the solution to the following problem. The search of the load that causes the numerical instability. With the term numerical instability, we mean the potential collapse of the structure. The structure has a linear elastic behavior before it becomes unstable, before the backlink occurs. And this is the following equation that describes the equilibrium of the structure. The term K0 corresponds to the stiffness matrix related to the small deformations, is not load dependent, whereas the K sigma is the stiffness matrix related to the initial stresses, is load dependent, and is a linear function of the load. In order to solve the equation of the equilibrium, the following constraint exists, which is basically the depth of this following quantity to be different from zero. So basically we search for the lambda values that causing this quantity to be equal to zero. It's basically similar to the model analysis where you're searching for the omega values. So in this case, we search for the lambda values. A typical case is the following frame when running the generalized backlink analysis in advanced design, you get all the different lambda values that each of them corresponds to a different backlink mode. So the lowest lambda value corresponds to the first backlink mode, and as the lambda values getting higher, as they are increasing, you get the different backlink modes. Obviously, the critical load, the lowest load that corresponds to the potential collapse of the structure is the external load multiplied by the lowest value of lambda. This is the critical load. This is the load that will cause the potential collapse if happens. A typical case where generalized backlink is studied again is this cantilever column. The section of the column is a UB 152 by 89, is 3 meters high. The external load applied is minus 100 and is compressive and is modeled as a beam element with 11 nodes. So in this case, running the generalized backlink analysis in advanced design, we get the lambda value, which is in this case 4.7. The software pretty much solves the following equations as they are presented here. And of course, the critical load that corresponds to this backlink mode, the backlink mode 1, is the lambda 1 multiplied by the external load, in this case 100. So basically, at 456.7 kilonewtons, this cantilever column is going to be buckled with the mode 1 of buckling. Let's move now to the second order analysis. The second order analysis covers the so-called P-delta effect, is the amplification of the internal forces by the deformations. In the majority of the cases, a first order analysis is needed in order to get effective results. When assuming a first order analysis, the following assumption is always on. The deformations are assumed to be relatively small, so all the equations of the equilibrium are described using the undeformed shape of the structural element. Looking at the first picture, here is a cantilever beam where two different loads are applied. A vertical load with the notation P and the horizontal load with the notation V. Assuming a first order analysis, which means the deformations of this structural element are relatively small, the bending moment at the fixed end of this element equals V times H. Assuming a second order analysis, which means the deformations are not relatively small now, the so-called large deformations assumption, the bending moment at the same structural element at the fixed end is now equals V times H plus P times delta. The bending moment at the fixed end is increased due to the effect of the vertical load on the bending moment. In this case, the equations of the equilibrium are not described using the undeformed shape, but they are described using the deformed shape of the structure, and this is the reason why the bending moment is now increased, because the load P, the vertical load, is now producing a bending moment for this fixed end. Let's see now an application of a cantilever column using the advanced design first order and second order analysis. In this case, we have a cantilever beam, and we see in the first case the bending moment equals 500 when using the first order analysis, whereas when using the second order analysis is slightly increased. Of course, the effect of the P delta effect and how much affects the bending moment is totally related to the magnitude of the vertical load, and of course to the magnitude of the produced developed deformations. The higher the vertical load and the developed deformation due to these loading conditions, the higher the difference between the bending moment of the first order analysis and the second order analysis. The second order analysis is an iterative process where the load is divided in steps with several iterations per step in order to have a successful convergence of the algorithm. The convergence is performed based on force, displacement, and energy. There are two different computational schemes that can be used in order to perform this numerical analysis. Either a complete interruption, where the stiffness is updated at each iteration, or a quasi-Newton numerical scheme, where the stiffness is updated at the beginning of each step, but not between the iterations process. The first option provides effective results, but the computational cost is quite high compared to the second one, where the computational cost is relatively reduced, but the convergence of the algorithm might be the case. A second application of this second order analysis functionality, using again the advanced design. In this following frame, we will monitor this particular section, and we will compare the results, assuming small deformations and large deformations. So in the first case, the bending moment of this frame when running a first order analysis climb up to 131 kilonewtons meter, whereas when the second order analysis is assumed, the bending moment at this particular section is slightly increased to 131.8 kilonewtons meter. Again, the same conclusion applies. The effect of the P delta effect on the bending moment is influenced by different parameters, so it's based on the user, on the structural engineer, to decide if they need to take into consideration any large deformations, or they are happy with performing a first order analysis and assuming a slight error due to this assumption of the small deformations. Let's move now to the nonlinear supports functionality. The nonlinear supports, it's a functionality that the user can find within the interface of the software, and in order to use them, the user needs to define a nonlinear analysis for the analysis and design of the structure. The advanced supports can be either a point support, a linear support, or even a planar support, and they can be used in order to model the behavior of the bridge bearings, the behavior of a flexible or a rigid pile, and even the behavior of the soil, in order to define a support that can be only compressive and not tensile at all. We will see now how to use the advanced supports to model the behavior of bridge bearings and the behavior of a rigid and flexible pile. In order to model the bridge bearings, the following advanced support needs to be used. It is named a gap support, and is basically blocking the requested degree of freedom after a limit displacement, as it is called within the interface of the software. So basically the user prescribes this limit displacement, and since this displacement is reached, then the support is activated and starts providing a force to block any further movement of the structure. As long as this limit displacement is not reached, the support is not activated, which means the structure can move between this threshold of displacement. Here are some characteristic curves for a gap support with a 2 centimeter gap and defined as symmetric without elasticity and asymmetric with elasticity. In the first case, the force is the same after the 2 centimeters are reached, whereas in the second case, the force is a linear function of the displacement, which means as the displacement increases after the 2 centimeters, the force is increased linearly. Here is some examples of steel bridge deck. In the left-hand side, on the left-hand side screenshot, we see the bridge deck when the supports are not activated, which means the horizontal displacement is below the 5 centimeters, and in this case, as we can see, the reactions are equal to 0 because there is no activation of the support, and of course, as we can see here, the displacement are below 5, and this is the reason why the supports are not activated yet. Whereas on the bottom figure, the supports are activated because we see on the left part of the deck that the support reactions are now higher than 0, and of course the displacement, the horizontal displacement on the steel bridge is equal to 5, which means the gap support has been activated and starts providing reactions in order to block any further movement of the steel deck. Let's see now how to model the behavior of a rigid and a flexible pile using the advanced supports functionality in advanced design. A rigid pile blocks every movement, both horizontally and vertically, in a structural element until its capacity is reached. Once its capacity is exceeded, the pile starts moving, sinking deep into the soil, causing the development of deformations and displacements in the structural element. The behavior of a flexible pile is quite similar to the rigid pile, with the only difference to be the allowance of some deformation before its capacity is reached. The hardening support option that exists within the advanced supports functionality in advanced design can model effectively the behavior both of a rigid pile and a flexible pile. A typical hardening support can be seen on this figure, where basically a limit force is prescribed by the user. This corresponds to the capacity of the pile. In this case is 500 kilonewtons, which means that every movement is blocked, of this degree of freedom is blocked up to 500 kilonewton. However, when this value is exceeded, any further movement is now allowable. On the right hand side, we see a typical force displacement diagram option as an advanced support. with an initial stiffness in order to simulate the behavior of a flexible pile in this case. Again, we see here the initial stiffness that exists, which is basically means that some movement is allowed before the capacity of the pile is reached. And since this capacity is exceeded, the pile cannot provide any extra force in order to support any further movement, and then any further movement is allowed. In both cases, we see that the diagram is not symmetric, which means that the pile, of course, works only when compressive loads are applied to it, and this is the reason why the diagram should be kept only on the negative part and not in the tensile part of this diagram. Let's see now an example of a hardening support using the advanced design. In this multi-story frame, a hardening support is applied on this node, and the difference between the frame on the left-hand side and the right-hand side is the load. An increased load is applied on the frame B in order to activate the hardening support. Checking the first case, we see that the reaction forces are equal to 4.6, and any movement is blocked because there is still capacity within the hardening support. As the load of the frame is increased, we see now that the limit force has been reached. I have prescribed the limit force of 10 kilonewtons in this hardening support when I modeled this frame. So the hardening support limit force has been reached, and the node starts moving. If we check the screenshot B on the right hand side, since the hardening support cannot provide any extra force in order to block any further movement of this node. We will see now how to perform a generalized backlink analysis using the advanced design, and also we will see how to perform a nonlinear analysis in advanced design using the tools we already saw during the presentation. I am going to perform a generalized backlink analysis for this frame. First of all, I need to establish the generalized backlink analysis and select the load I need to take into consideration in order to perform this analysis. And I need also to define the modes I would like, the number of the modes I would like the software to provide for me, and then I need to run the analysis. On the results tab, I can access the backlink load case here, and I can also see all the different modes with their lambda prescribed next to them. And by selecting the load case of the backlink, I can see the different modes. This is mode 1. I can, for example, check mode 4. So this is the fourth mode of backlink. In this case, I have asked for the first 10. So for example, I can click on the 10th one and see how it looks like in terms of the displacement, the depiction of the mode of the different backlink modes. Let's see now how to perform a nonlinear analysis in advanced design. I am going to perform a second order analysis. I'm going to use the nonlinear functionality of the software in order to ask the solver to perform a second order analysis. This frame has already been designed within the interface of the software. I have applied both horizontal and vertical loads, and I'm going to set up now the nonlinear properties in order to perform a nonlinear analysis. A nonlinear static analysis is selected. I am going to enable the large displacements because I would like to take into consideration any P delta effects. I would like the solver to use the deformed shape of the structure in each step to describe the equations of the equilibrium, and I'm going also to select which load case I would like to consider for this nonlinear analysis. In this particular model, I have applied only dead loads, so basically the dead load case or any of the combinations here can be used. I'm going to select the dead loads only for this particular analysis. Here are some parameters that can be changed when running a nonlinear analysis. It has to do with any coefficient associated with the load, the number of iterations that the solver is going to perform, the number of steps. The number of steps is related to the proportional amount of the load that is going to be applied when the solver is going to perform the Newton-Raphson numerical method in order to identify the response of this frame, and the number of iterations has to do with the convergence of the numerical scheme, and the solver has the option to keep either the last step, which means the last step when running the analysis, or if selecting complete, the entire process. So somebody can plot a P delta curve, for example, a force displacement curve, and see all the different stages of the equilibrium of this particular frame, and identify the different response throughout. And finally, there is the option to run a quasi-Newton or a full Newton-Raphson methodology scheme, a numerical scheme. The full Newton-Raphson updates the stiffness matrix after each iteration. It produces better results, but it costs computationally. On the other hand, the quasi-Newton numerical scheme does not update the stiffness on each iteration. It might affect the stabilization of the whole process and might trigger some instabilities, numerical instabilities, but it can save computational time. So it depends on the user, after all, what they feel or what they think is appropriate. The energy, the force, and the displacement is related to the convergence of the algorithm and can be defined either by the user or can be left as the default options here. And now I can run the nonlinear analysis here. I'm going to run only finite element calculation at this point. The calculation has finished, and now I can access the results from the results tab here. So I am going to request both the linear response and the nonlinear one. As you can see here, the nonlinear response appears as, if I can use the term, another load case on the results tab. So you have the access to both of them and compare them at the same time. And now I'm going to plot the deformed shape of this frame. So this is the deformed shape of the frame when the dead load has been considered to act non-linearly on the structure, whereas this is the deformed shape of the frame when the dead load is acting linearly. We can check also the bending moments, for example, for this frame and see the effect of the P delta effect. This is the linear response, and this is the non-linear one. Before closing this webinar, I would like to summarize the key points of this short demonstration. First of all, the nonlinear analysis can be performed very effectively within the advanced design interface. Some functionalities that can be very useful is the generalized backlink, the second order analysis in order to take into consideration any P delta effects. Several parameters related to the nonlinear analysis can be modified by the user, facilitating the entire process. We saw earlier that the user can define the numerical scheme used, can change the number of steps and iterations when running a nonlinear analysis. They can even change the parameters that are related to the convergence of the algorithm and the stabilization of the entire numerical scheme. And finally, the use of advanced supports requires nonlinear analysis to be performed and can be very useful for modeling the response of engineering applications, such as the bridge bearings, rigid and flexible piles, soil response. Thank you very much for your attention, and I'm happy to see you again in one of our webinars. I'm happy to take any questions. Thank you so much.